The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney. Welcome back. Today we have on the podcast Misty Wall, who is a member of the technical staff at the Unitary Fund. Before that, she worked in the rather significant topic of extreme ultraviolet lithography at ASML. She is a primary contributor on the Mitiq project up on GitHub, which is it's a package for error mitigation for quantum computers. Really interesting project.
Yeah, it's fantastic, Kevin. I'm looking forward to talking to Misty. I've been tracking the Mitiq project from the very beginning in 2019. It was brought to us at IBM when I happened to be working for IBM Quantum at the time by Will Zhang and Nathan Samuth, who were the founders of the Unitary Fund. We thought it was a really interesting project at the time, and it's now it's matured quite a bit and made a lot of progress. They've been releasing papers, research papers on the archive based on using Mitiq for error mitigation and getting some really interesting results. And more importantly, I think as a phenomenon, Mitiq and the Unitary Fund represent sort of maturation of quantum computing as a field. And we've talked many times about how quantum computing is coming out of the physical sciences, quantum mechanics, quantum physics, quantum information theory, and it still is. Is very rooted in fundamental science and basic research, but is increasingly moving towards being a technology that requires engineering discipline and the kind of measured progress that you see in emerging technology and other fields of classical technologies. And I think Mitiq and the Unitary Fund and the work that Misty's doing are really good examples to see exactly how that dynamic is playing out today and what the advantages are of that kind of an approach. Welcome back. We're joined today by a very special guest. We're excited to have her with us, Misty Wall. She's a member of the technical staff at Unitary Fund, which is an open source quantum software foundation. They do micro grants, and also they are leading the development of a project called Mitiq, which is a framework for error mitigation of quantum calculations, quantum computation. And Misty, very good to have you with us. Thank you for joining us, and welcome.
Thanks for having me. It's
Welcome,
great to be
Misty.
here.
Yeah, good to have you on.
So if you could start off, Misty, with just some background as to, what is a member of technical staff at Unitary Fund? What is your role? And how did you get to that role? I think that, we've said it many, many times before, everybody has a very unique path into the quantum computing field. We always love to hear the sort of personal story.
Sure. Well, I in particular do a combination of software development, quantum software development, and also research in quantum error mitigation. We do a lot of different things. Some of our staff members emphasize other aspects of research in quantum computing. But the common thread is open quantum software, open source, and also community building and education initiatives in quantum.
Awesome. And was your background, Misty? Did you study quantum physics? Did you come more through the computer science direction, or how did you get here?
Actually, I have a non-traditional background.
Excellent.
So my degrees are in mechanical engineering. I started out as a mechanical engineer.
Oh, cool.
I worked for a semiconductor equipment company called ASML.
Right.
And I was there for 9 years. I started out as an engineer, but then I moved into project management. Then I kind of, from hardware, I went into software project management. And I was kind of at a crossroads in my career and figuring out what I wanted to do next. I knew I wanted to become more of an individual contributor, and I was trying to figure out what I wanted to emphasize, what I really wanted to study, and I heard a talk from IBM on quantum machine learning, and I realized, okay, that's the grand challenge that I want to pursue and next, and I wasn't really sure how to get in. So I was doing a lot of like self-study, doing different courses online. I went through the MIT Pro Certificate program that quite a few people who've kind of followed this non-traditional path in the field have done. And that was like during the pandemic, early 2021. And after that, I wanted to continue my learning journey. And so I heard about Unitary Hack, and I signed up for that. And I ended up contributing to Mitiq through that and learning about quantum error mitigation and learning about quantum software development through that experience. And I would say most importantly, connecting with the team and getting that mentorship, being part of the community. And it just kind of happened really organically, building up those contributions and strengthening those connections. And then in March of last year, I became a full-time member of the technical staff, working on quantum error mitigation at Mitiq.
Awesome. And just to rewind for a second, so ASML famously is the tool supplier that uses extreme ultraviolet, right? Lithography for the 2 nanometer
I worked on
chips.
That program.
Did you? So, so that was a solved problem. You decided you wanted to go find something else that was more challenging than extreme ultraviolet lithography. Okay, I guess.
I mean, it was an amazing experience, and I definitely learned a lot. And definitely, I can see parallels between doing something that's never been done before. A lot of people didn't believe that it could be done, or at least that it could be industrialized the way it ended up being. And I contributed to that program. And then, as it started to mature, I was starting to think about, okay, what's the next thing? And I mean, not to say that quantum computing is the only next thing, but really looking for that, okay, what is it that's going to be at the cutting edge? And it just really clicked for me when I heard about quantum computing.
You usually have a taste for a stern and formidable subjects, right? It's like Mechie is a no nonsense degree, right? ASML, man, they're doing it right at the limit, and then quantum computing, not a walk in the park.
That's true.
I suppose it's a theme.
Yeah, exactly. Yeah. That's very cool. And Unitary Hack, it's really a unique event that Unitary Fund holds. I think it's in early summer, right? May or June, something like that. And essentially, anybody participating, any company or entity participating can tag issues in their GitHub repos with Unitary Hack, and then participants can just grab those issues and try to solve them. So was your entry point more sort of, classical software development? You were sort of squashing bugs that were more classical in nature, or were you already sort of addressing the quantumness of the Mitiq framework?
I already went and just dove in to the quantum part as well. I was actually pretty new to software development at that point. Wow. And so it was, I was learning everything at once. I mean, I certainly had done programming before, but not like that, not, for other people to use. It was kind of my own scripting before. And so
product versus tool, right? Like your own homegrown tools versus something that somebody else is going to use. It's definitely a different challenge. So that's that's many learning curves at once. It's pretty impressive. So what was it that drew you to the Mitiq framework?
Well, part of it really was, at that time I didn't really understand much about quantum error mitigation. So I was really looking for something that would, that really did address the quantum aspect as well as the software aspect. And so I saw that I actually joined partway through the hackathon. So it was also kind of like, okay, what are the remaining quantum related issues here? And this was one where it was actually applying Mitiq ZNE to a VQE problem and kind of showing that Mitiq helped converge faster. It turned out that this was actually more of a research project because at that point, no one had really tried that exactly with Mitiq before, and so similar things, but not that exact problem. And so it actually took some time beyond the hackathon to really get that.
And just for the benefit of our audience, you mentioned VQE as those variational quantum eigensolvers, right? That's one of the major algorithms. But they must be very sensitive to error propagation, huh? So they
can be,
yeah. So kind of
enhancing
cool,
the convergence.
Cool outcome
error
right there.
Mitigation.
Yeah.
And so Mitiq is a framework that allows for multiple approaches or bring your own approach, really. You can build your own approach for error mitigation. The one that you first started working with was zero noise extrapolation. Can you describe how that works at a high level?
Right. So zero noise extrapolation is kind of like, it works in kind of two stages. So what you're doing is you're changing the noise level of the computation by manipulating the circuit in some way. And you do that a number of times at different noise scale factors. And then you extrapolate from evaluating at those different noise scale factors, you get different expectation values from your computation. And then you extrapolate back to the zero noise limit. So you say, what would be the expectation value if there were zero noise?
Right.
And so there are different ways of applying ZNE. So the first way it was done was through something called pulse stretching. And so kind of like increasing the duration of the pulse so you get more noise in the computation that way. And then the Unitary Fund did something called digital zero noise extrapolation. And so there you are actually inserting extra operations in the circuit. We call that unitary folding. And those operations, ideally, they compile to identity. But in reality, if you implement them on the device, they're going to increase the noise level as well. And so if you do that many times, then you get a lot more noise. And so then you're kind of further out on your curve. And so you get this nice curve that you can extrapolate back.
Oh, that's fascinating. So what you're saying is that by introducing noise on purpose, you're able to then create a curve from which you can extrapolate down to an optimal value.
Yes.
Super cool.
Yes.
That's cool.
And you can actually...
Go ahead. Sorry.
You can actually do it in the other direction, too, through something called probabilistic error reduction. And so that's a framework that some folks at Unitary Fund also came up with, the noise-extended probabilistic error cancellation and virtual ZNE. So you can actually use that to instead reduce your noise level, and then you have these also noise-scaled values, but they're lower than your kind of baseline computation.
That's interesting. So I was going to ask, you talked about either stretching the pulse or introducing additional pulses. Is that related in any way to something I've heard of called dynamical decoupling, which is introducing random pulses in between gates in a way that sort of counteracts the noise that builds up when there's no operation on a qubit?
Well, that actually works a bit differently.
Okay.
So that's kind of... so that's inserting pulses in idle windows. I mean, it's still all of these operations, in the ideal case, they compile to identity. So it's kind of the same idea of like, you kind of have an equivalent circuit in the ideal case, but in the noisy case, you don't, and it should help your result in the end. But for dynamical decoupling, it's more about keeping your qubits busy so that they don't kind of wobble around in idle windows.
I see. And for zero noise extrapolation or probabilistic error reduction, how much work does Mitiq save someone starting from scratch to implement that or some other error mitigation strategy? I mean, it's a reusable framework, right? So it is. Yeah.
I mean, it's designed to you can apply it in a few lines of code. Of course, if you're working with hardware, you may need to tune the parameters to actually, see the improvement that you want from Mitiq. So we are actually working on a calibration module, and we've released the first version of it. And so it's kind of automating some of that parameter selection.
Oh, cool.
Where we have some predefined circuits, and then the user can run the calibrator, and that will kind of give them some intelligence on what are the best parameters to select.
Interesting. That's cool.
It kind of sounds like, TensorFlow or PyTorch. I mean, it can save you some time, but you probably should know what you're doing first before you. Yeah.
We have a lot of great examples in our documentation, though, so I would really encourage people to check those out.
That does remind me of one of the questions I just thought of. Is, I mean, if somebody is listening, and I'm certainly warming up to this idea myself of wanting to get into Mitiq and do some just fun goofing around with it. What would be a good pet project for them to sort of take on as a first sort of like hello world in error mitigation?
I would definitely try reproducing some of the examples in our documentation. We have some really simple ones for CNE. I think zero noise extrapolation is the easiest to understand conceptually. It's also the easiest to set up.
Yeah.
So I would say start with those. We have a number of kind of like variational algorithms, and you can, play with different parameters, change the noise level, see how, try different noise scaling techniques, and start to get familiar with what are the options and how does it respond. And then I think you can build up from there.
Sounds cool. And it's MIT IQ. It's up on GitHub, right?
Yes.
So
MIT
easy to find.
IQ.
Yeah, right. Yeah.
Or Unitary.fund as well, I think, right? Yeah.
You can also find it through Unitary.fund.
Yeah.
Cool.
And actually, we have the Unitary Fund organization on GitHub, and then Mitiq is under that umbrella. It's one of the repos in our organization.
That's cool. Do you find, I mean, you're coming to this from a non-traditional starting point, so it may be hard for you to reflect on this, but it occurs to me that like most researchers are not building reusable tools while they're doing their research. And I'm just curious, like most researchers are doing something, often it's whiteboard based. Maybe they write some circuits that they run on simulators or maybe actual hardware. But it seems like the Mitiq project is doing research while developing, as you said, project or product code for other people to use. I'm just curious if you have any sense what that does to the research process or the research, the quality of the deliverable. I mean, it feels like your deliverable is reusable code immediately, which is not usually the case with academic research.
Yeah.
That's true. Yeah. Although I think we are starting to see more labs open sourcing their code, which is really encouraging. And even the things that we don't release as part of Mitiq, or at least not right away, are open source on our research repository. So our research repository is public. It has all of our code and data there, mostly in the form of notebooks. But anyone can download those and run them and, even kind of contribute to those if they want. It's definitely different. I think, it does encourage, better standard of code. And I think it does, we do have to think rigorously about what we're implementing and why. And I think that's really helpful in research. I think it also helps in the writing process of explaining what we did, why we did it, why it's important. I think it's a great tool. We're also seeing, a number of applications like quantum simulation papers coming out that are using Mitiq. Not so much error mitigation research, which is interesting.
It is.
I think error mitigation researchor, they have their own code at this point, and they're using that. So,
interesting.
So interesting.
We definitely want to.
Yeah. I'm sorry to interrupt. I was just wondering, I mean, one of the big themes we keep hearing on the podcast across multiple episodes is how some of these new frameworks in quantum computing could be either applied to actually running, experiments essentially about physics and the way the universe works, and or these same frameworks are excellent at getting new insight on the actual physics of an individual machine, a specific quantum computing architecture. I mean, I wonder to what extent some of these zero noise extrapolation algorithms might inform either of those two threads of investigation. What do you think?
Well, I think it can be. I think it can be both, actually. I mean, with ZNE, it's kind of something where, we're kind of applying it after the fact. So I think we're getting limited information out in terms of the noise characterization there. So I want to be careful in terms of the performance of the device. But what we can see is that if we think about something like quantum volume, like you can actually enhance quantum volume experiments with zero noise extrapolation. And we've actually done that.
That's
we
pretty
have
cool.
a paper up on the archive about that.
Yeah, cool.
I'm just imagining there could be different curves of your ZNE response depending upon the class of hardware that you're dealing with. And so, I don't know, there could be cool comparative measures you could make there with respect to how different architectures have strengths and weaknesses.
Yeah, actually, and to that point, does ZNE or probabilistic error reduction, do either of them work better on superconducting versus trapped ion versus another modality of qubits, or is it pretty much neutral to the underlying implementation of the hardware?
We have seen different results on different modalities and different devices. I don't remember off the top of my head which is good for which, but we do actually have a paper on that as well, where we test a number of different
and I was going to say,
backends.
That begs the question, actually. So what backends are supported through Mitiq? What hardware can you run Mitiq on?
Anything, pretty much anything. It's about, can you then convert, the quantum program to whatever the backend will accept. But we can wrap pretty much anything as long as it's in a supported front end. And we support the major front ends, so like Qiskit, Penny Lane, Bracket, PyQuil.
Yeah, cool.
And Circ, of course, we're written in Circ.
Yeah. And I guess, it sounds like, though, pulse control would be required for the back end. You'd have to have access to pulses in order to properly implement it. Is that right?
No, actually. So I want to clarify, Mitiq is gate-based. So it's gate level, that is. So you don't need pulse control. Of course, that means that sometimes your error mitigation may get compiled out.
Right.
So there are certain things where you have to specify that the optimization level should be 0, or maybe, if you have some control over what kinds of optimization are done, you need to do that.
Right. But you said pulse stretching was one of the ingredients in zero noise extrapolation, I think, right?
Originally, not as implemented in Mitiq.
Oh, you said it's moved to a digital, meaning gate-based approach.
It was moved to a digital abstraction.
Got it. Interesting. That's very cool. So, I guess, there's when you think of the path towards fault tolerance, there's sort of like basic qubit quality, and then one qubit and 2 qubit gate fidelities, but then there's sort of the hardware level, fault tolerance, error codes, surface codes, and LDPC, and those types of things, and then there's sort of a level of abstraction. That's where error mitigation or other potential strategies would come in. Do you see that sort of continuing to have a role over time, or do eventually you get to sort of this idealized state of the hardware and you don't need to worry about mitigation anymore at the software level?
I think you'll always have errors. You'll always have quantum errors, and so you will always want to try and enhance your results. So there will always be a place for error mitigation as far as we can see. And in fact, I think error mitigation is going to be very important in the transition to fault tolerance, because it's not looking like one day we're just going to flip a switch and quantum computers are going to be fault tolerant. But as we make these incremental gains over time, we can use error mitigation at every step to enhance the results.
Right.
And I actually worked on a technique combining quantum error mitigation and quantum error correction. And so that's scaling the distance of the surface code.
Oh, cool.
Or of the error correcting code in general. And then using that as the noise scaling method for ZNE.
Isn't that your latest paper that was just?
That is my paper.
Yeah.
That I recently presented at IEEE.
Fantastic.
Very cool. So say more about that. So the distance is important in error correcting codes because that has to do with the degrees of that you can degrees of error that you can correct. Is that right?
Yes, that's correct. Yep. And so if you have like a low distance, the idea is if you're below the threshold, that's the caveat here, but if you're below the threshold, then you can, your low distance code, you're going to have like more error. Higher distance, you're going to have less error in general. And so you can actually use that as the scaling knob. So you can deliberately say, I'm going to encode at a lower distance. I'm going to have more error in my calculation. Then I'm going to encode it at higher and higher distances until I'm at the capacity of the device. And then I have these noise scaled expectation values from each of those computations. I can extrapolate that back to the zero noise limit. And now I have a more accurate expectation value than I would have had I just encoded at the highest distance I could, and then that's it. That's the error rate. So it can get this lower effective logical error rate by using this technique.
Interesting.
And it actually showed that you can do that.
Does that help with the efficiency of the error correction scheme as well? And in other words, there's an overhead of, a ratio of X physical qubits to Y logical qubits, and that ratio can be very, very high. So does this help you sort of achieve better results with a smaller number of physical qubits per logical qubit?
Yes, because one of the tricks that you can play is you can actually run certain parts of your computation in parallel. So you can run like different circuit instances. Of course, if you have like modular circuits, you have the right size device, you can run your computation in parallel. You can take additional samples at these lower code distances because you've freed up the capacity of the device at the lower code distances. And then as you go up, you can take fewer samples, but you have less error. And so you can also use that parallelization as an additional knob. So you can kind of smooth out some of the noise in that way as well, and kind of adjust like where the points are on the curve and optimize your extrapolation in that way.
That's a really good example of how error correction and error mitigation are going to need to sort of be used in collaboration with one another to get better results over time.
Together with big volume.
Yeah, exactly.
Yeah.
And something else occurred to me. So are we talking about all errors, or is this phase flips or bit flips? Like, is it more suited for one type of error in qubits than the other, or is it just errors generically?
Just generically. Okay. Yeah, we use a pretty simple error model for the demonstration, but certainly extensions of the work could be like you could actually simulate, surface codes or STIM or something like that, and try the same thing and see how that performs, or assume that you have a different kind of error correcting code. Right. You could assume different distances throughout the circuit. We didn't turn all of those knobs. We were just proving the concept.
Yeah. That'd be interesting because, certain physical qubit implementations like cat qubits, for example, are more resistant to one type of error versus another. So it'd be interesting to see if this hybrid approach to mitigation plus correction is more effective in one scenario or another.
I'm wondering if I could go on a limb here and perhaps encourage you to speculate a little bit. It's I don't want to put you on the spot too much, but this is one of the things I do on the cast. Is that the threshold theorem, naively stated, right, is that there's a certain threshold of error correction, error mitigation, above which we can get to essentially fault tolerant computing, and it's been a big couple of years, right, in those algorithms and advances. Among them, the work that you're doing. What do you think? Is it within sight some outcome where quantum computing could get to a crossing that threshold and be ready for prime time, or are there still many breakthroughs left to hurdle over before we're in the end zone, so to speak?
I think we still need many more qubits and much better qubits. But I think, that's a big part of why we're doing what we're doing, is that we need all of these ingredients. Like, we need better error correcting codes, we need error mitigation, we need better error mitigation techniques, and, we need this to be as open and as accessible as possible to really make those kinds of breakthroughs.
Yes, yeah. And here it is again. I mean, if you could speculate, could you try to put a time frame on that one? I mean, I know our audience is curious. I mean, what do you think? It's a few years, 5 years, 10, or maybe my kid's lifetime?
I mean, I've been hearing 10 or more.
Yeah. Still, it's exciting to hear that it's within. It feels like it's within grasp in some reasonable amount of time. It's not just some science fiction remote outcome. Really interesting.
I think grand challenges are usually measured on the order of a decade, right?
Yeah, that's right.
That feels right.
Yeah.
And if it were any shorter, maybe.
How grand is 3 years?
Yeah, right.
You talked about Unitary Fund being about community building as well. What is it? How does Mitiq itself get used to sort of build open source quantum community?
Well, I think a big way that we do that is actually through our community calls on Discord. So anyone can join those calls and just interact with the team,
cool.
Audio, video, whatever they're comfortable with. We also have forums on Discord. We have discussion forums on GitHub. And so we have a lot of different communication channels, and anyone can join. We welcome people to join, beginners, all levels, all backgrounds. And I've definitely seen a lot of people get connected with us, and I got connected with Unitary Fund through doing that. Also Unitary Hack, like having events like that where, there's a lot of buzz and, a lot of people around and kind of trying to figure out what's going on, and, another inroad for people to see like what we're doing. And it's all open. It's all, very accessible. So people can start to get a sense of that and see where they would like to contribute.
So cool. And Unitary Fund is a 501c3. Yeah. Is that right?
Yes, it is.
Interesting. Wow, impressive. And so how do the economics work? I mean, there's a core team of competent, ambitious people. There's some funds allocated towards, I gather, promising researchers. Mm-hmm. How does the basic economics of the Unitary Fund work?
Sure. So we do a few different things. So there's our internal research and internally driven projects like Mitiq and Metric. And so that's funded through government grants. And then there's the micro grant program, and that's funded through corporate sponsors and individual donors.
Fantastic.
Mitiq actually was partly funded by a corporate sponsor. It was me. It was largely a government grant, but there was some additional funding that was required that I convinced my employer at the time, IBM, to foot the bill for, because we really liked the project when Will brought it to our attention. So I was quite happy to be able to help get that off the ground, because I just think it's amazing. Is there, I guess, there's the open source projects within Unitary Fund have, I think, all been, at least the ones that are micro grant or internal projects, have all been software sort of on the application side, right? Circuits or compilation or error mitigation. I'm wondering, I mean, I know that there's been discussions about doing more open source hardware, and I just wonder, what would the impact, or what would Mitiq be able to do if there was an open source, say, control platform for qubits that was also under the open source community umbrella?
Yeah, well, actually, recently we put out a paper on open hardware as well.
Right.
So kind of a review of all of the efforts that are ongoing, or many of the efforts that are ongoing in the field. So I encourage people to check that out. But yeah, I think definitely, we could have, lower level control that would, give us a lot of flexibility in terms of the techniques that we could apply, and also our understanding of, how well those techniques are working at the hardware level. Also, more noise-aware techniques.
Right.
So getting more of that feedback kind of lower in the stack would be fantastic.
That open hardware phenomenon, that's so cool too. I'm a little bit of a DIY crafter guy, and the onset of microcontrollers that were consumer affordable. And it's just that the whole maker scene exploded and was just energized so immensely by that. Again, this is no speculative thread here, but to what extent do you think it's possible that there could be at least some element of home DIY?
Kevin wants a qubit at home.
Exactly. Quantum computing rigs, right? And I know lots of the gear is insanely expensive. There's no way you would run a dilution fridge in your basement unless you're crazy wealthy.
Can you spell Raspberry Pi with a Q?
Exactly right. Yeah. It feels like there's stuff happening out there. Have you seen anything along those lines that might summon optimism for the ambitious maker?
Yeah, I think you already said it. The infrastructure around, quantum computers is pretty expensive, to say the least. But I think maybe some of the kind of more like the control electronics or, other, supporting components, that could be an opportunity for people to play with those and develop those. It's all important.
Right. I'm aware of Kik and Cubic, and I think Kik has a channel on the Discord now, and they're both using Xilinx boards with FPGAs to control superconducting devices, I think, or maybe even more than one type of device.
Superconducting, yes.
And those are both Kik is from Fermilab, and Cubic is from the Lawrence Berkeley National Lab. So both really interesting open source projects, and that's exactly what I kind of had in mind. Is I'm imagining what the Mitiq framework would be able to do if it had integrations into an open source control platform, and there was the ability to some future iteration of ZNE or probabilistic error reduction or some other approach that was actually reaching down into the control platform and using the native capabilities of that piece of hardware as part of the error mitigation. It seems like that opens a whole bunch of other doors for future directions.
Definitely. I think one important prerequisite for that, though, is that we really need to integrate with something like QIR or MLIR,
right?
Which is definitely on our roadmap, and is going to be a big effort, but definitely a worthwhile one. So
those are intermediate representations. Can you explain why that would be important?
Yeah, so part of it is that you want to be able to have greater interoperability in your quantum programs. So you want to use these intermediate representations. Also, including more classical programming elements. Right now, most quantum front ends are pretty limited in terms of what they can do when it comes to classical programming. And so having that all together in one framework would be very helpful. And then that would also allow us to talk to the control hardware a bit more easily. So
in a way, like the gate-based circuit that you would produce in Mitiq would be then translated into this intermediate representation so that it could be executed in whatever way is appropriate for the hardware, right? It is literally a go-between, an intermediate between the high-level circuit and the low-level execution.
Well, that would be the prototype, I would say. But ultimately, we would probably want to look into applying error mitigation at a lower level, like in QIR. Mm-hmm. Gotcha.
Okay, so that would, if you supported something like you said, MLIR or QIR, then you'd be able to incorporate those lower level controls in your error mitigation techniques.
Closer to it.
Got it. And would that be just another evolution of ZNE or probabilistic error reduction, or would that be new approaches to error mitigation, or both?
I would see both.
Yeah.
Definitely, we would want to start with what we know and what we can test easily. But I would hope that would open up a lot of opportunities to apply different error mitigation techniques or even develop new error mitigation techniques. I think right now, a lot of the reason why Mitiq is designed the way it is because of some of the limitations that exist in quantum programming right now.
Right.
And what we're able to do with the front ends we have, their limited interoperability, and we're already able to do quite a bit. I mean, Mitiq can convert between different front ends. It can accept pretty much any back end. But there's a lot more that we could do if we were able to operate at a lower level.
Interesting. Cool. Are there theoretical error mitigation strategies out there that you are thinking might be next on the Mitiq roadmap?
I think one of the really interesting directions is some of the machine learning quantum error mitigation techniques that have been coming out recently. So I think you'll be seeing more of those.
No doubt. That same phenomenon appeared several times in the podcast. That's a huge frontier. Really fascinating too. Huh?
Yeah.
Yeah.
That's cool. So with that, can you describe more how ML might be used in error mitigation?
Well, I mean, there's a couple different ways. I mean, one is kind of, learning your error mitigation parameters. You could also think about, noise-aware techniques. You could think about different ways of compiling circuits to kind of optimize for noise. So it's kind of all part of the same thing, but like looking at the, slightly different parameters, whether you're talking about like circuit compilation in general, or you're talking specifically about inserting gates in certain areas, or scaling up noise or scaling it down. And yeah, there's a lot of different possibilities.
Well, one might speculate that the ZNE technique could be more complex curves of response that would perhaps elicit the need for more advanced algorithms beyond regression to find a 0 point. Who knows?
Definitely. But I think there's also many more areas to explore in terms of QEC, inspired quantum error correction, inspired techniques, and those could also benefit from ML. So there are a lot of possibilities.
If you had pulse level control over a qubit system, would there be potentially like ways to train ML models to tune the pulse schedule for particular gates, or even sort of have undirected pulse control over the qubit and just tell it what result you want, and it sort of hacks at it until it comes up with something? Just guesses billions of times until it comes up with the right way to get the logical result.
I mean, that's, it would be great if we could do something like that. I think something, there are probably, quite a few steps are needed to actually get to something like that. But that's a great future vision for error mitigation, I would say.
Very cool.
This has been really fun, Misty. Yeah. We really appreciate your time. Thank you.
Yeah, thank you. And
thank you for having me.
No, our pleasure. I mean, it's a great project, and Unitary Fund is a terrific organization. And I mean, I think Mitiq is such a great tentpole in the open source community that's emerging in quantum. I think it's fantastic work. So thank you very much.
Yeah, thank you so much.
Thank you.
That was great. I mean, Misty, she's really an impressive person. I mean, to start with a MEC degree, I mean, that's a no mess around. Your base camp to start with. And then she jumps into UV lithography. And then, wow, I guess she self-taught herself on software engineering while simultaneously learning quantum mechanics. Not bad.
Not bad. Extreme ultraviolet, Kevin. Not just ultraviolet.
Not just UV. And now she's doing research on quantum error mitigation. It's pretty cool.
It's very cool. Yeah, no, that was great. And I really liked getting more in-depth sort of background on zero noise extrapolation, probabilistic error reduction, and especially that latest work that sort of combines error correcting codes at the hardware level with error mitigation strategies. So that really suggests really interesting future possibilities for the Mitiq framework and for the error mitigation field itself.
No doubt. And it was fun just, I don't know, messing around a little bit on the topic of my dream of there someday being, home DIY quantum computing open tech, someday.
We'll get there. You'll get your little tiny dill fridge or your really high power lasers, your optic table in your kitchen.
Doesn't that sound like a good time?
Absolutely. Yeah. Absolutely. We'll get there. All right. Thank you so much for joining us. Until next time.
Thanks.
Okay. That's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.